Next we have pattern recognition. So, what is pattern recognition? It is a process whereby a received pattern, or I would say a signal, is assigned to one of the prescribed number of classes. People are familiar with pattern recognition, right, and I think this is a study over the last possibly 50-60 years of signal processing. A good example for a pattern recognition task is, suppose I give you isolated words. People are speaking 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, right. These words people are talking, and I want to form a digits, right, 123, 123, 145. I want to form these connected digits in some way. And as I am speaking these words, can a machine recognize that a 1 is a numeral 1, a 0 is a numeral 0, and so on. For example, as we are talking through our phone and we are keying in some account number or some details, and the machine should automatically recognize the numbers from the spoken speech. How can we do this, right? And it has to do some control, some actions post that. This is one important application of AI, right. This is pattern recognition. So, how does one do pattern recognition? First is what we have inputs, right. Inputs are normally signals, right. In this could be like speech, images, videos, etc. The first step is to extract the features out of these inputs, and this is called the feature extraction phase. From the feature extraction, we get the feature vectors, and the output of the feature vectors is fed into a supervised or possibly an unsupervised network for classification. And then you have outputs. So, going slightly deeply, what is happening here? We have some signal X, and this is in an m dimensional observation space. So, I just say Rm. From this space, I get into a feature space which is q dimensional. This is Rq, and typically q is less than m, and let us say this is y, and from y I get into an output space which possibly has a tessellation, right. This is a t dimensional output space. So, at this stage, when you are taking your vectors from the observation space to a feature space, you are doing some kind of dimensionality reduction. For example, think about it in a simplistic speech recognition task, right. I have speech signal, speech is band limited, to 4 kilohertz, I sample it, and from the sampled speech I have to extract features. I may get the Melk-Ebstrom coefficients, or I may extract the Parkor coefficients or some feature set out of these, and these feature sets would be in a lower dimensional space than the input space, right, and these feature vectors are then fed into a neural network or a pattern recognition or any stochastic engine. In this case, since our interest in this course is neural networks, we feed this into a neural network which could be supervised or unsupervised, which provides a kind of tessellation at the output space depending upon what features are presented to it. That means I have a label and I have to associate this feature vector to a certain desired response. In the case of supervised, or I naturally tessellate the feature vectors in an unsupervised manner, and once I get the test inputs, I feed this to this network and then I can figure out which label it belongs to, right. That is a simplistic example of how this pattern recognition engine works. Let us now talk about functional approximation. Suppose I have an input x, this is a vector, and the desired response is d, which is the output, and this mapping f is unknown, right. I take an input which can be a vector, it goes through a function on this vector and it gives me an output. Now I do not know this function f, which is unknown. All I know is mappings. I know if I give x I get d, I give x1 I get d1, I give you x2 I get d2, so on and so forth. I just give you some samples and some desired vectors. The goal of this problem is as follows: design a neural net such that it creates a mapping, I call it capital F of x, such that under some norm measure capital F of x minus small f of x is within epsilon for all x. This is the functional approximation problem. That is, we do not know the unknown function, it can be nonlinear, time varying, etc., etc. We want to approximate this function using some other function capital F of x, and this neural network through non-parametric means can provide you this approximation, right. And examples for this functional approximation problem include system identification and inverse modeling. Well, one can think of inverse modeling as same as system identification, because I want to identify the system, but we want to segregate it into these two classes A and B, because for example, if you think about a nonlinear plant and you want to identify the system for control purposes, etc., then we want to treat this as a system identification problem. And inverse modeling, for example, if you think about in equalization in channels, etc., and you do not want perfect equalization, but you want a neural network to kind of approximately equalize, then we think about the inverse modeling. Perfect inverse is not possible, but within an epsilon tolerance we kind of settle to what we want, right. So this is an important task. So this is applications in communications, many things, right. And one of the important things that you have to understand is, in the case of neural network, there is no prior model, except that you have these biases and weights, etc. These are the parameters of the neural network, and you want to learn these parameters, and you do not make any assumption about the prior distribution. So, therefore, this is non-parametric form, whereas in the case of statistical signal processing techniques, it is parametric because you assume certain form for the density and you estimate those parameters using certain techniques such as maximum likelihood or MAP, maximum a posteriori probability, etc., etc. But in this case it is non-parametric. This is a very important distinction. So, let us look into a system identification problem, look at the sketch of what the building blocks are to realize a system identification problem. So, let me sketch the architecture and then I will explain how this works. Okay. So, this is a block diagram schematic of a system identification task. So, we have a input vector that is fed into an unknown system. We do not know how the system is a nonlinear system. It gives us a desired response d sub I, and then we feed this input vector also to a neural network. This gives us a desired response y sub I. We take the difference between d sub I and y sub I, that gives us the error signal, and a function of this error signal through the objective function is what drives the adaptation of this network. Of course, if you are slightly savvy, you may even wonder and ponder if the desired response and this y sub I have to be scalars or vectors. They could be vectors. You could have vectors. If you have vectors, then you have an error vector, and if you have an error vector, you convert that vector into a scalar by an appropriate norm measure and then drive the network under certain regulatory conditions. We will talk about these details as we set up the problems carefully, but this is more a qualitative feel of how a system identification task can be accomplished. Similarly, we have inverse modeling. So, we have an input vector that goes into this unknown system which we do not know. Let us call this f. It gives us some d sub I, which is the system output. But I think what is important in this block is this input vector is also a sort of it is provided to this linear combiner here in this, which is you have y sub I in one path you have the input vector in the other path, you take the deviation, you get the error E of I, and that drives this model, right, because we want to model this unknown system, and what we want is we want y of I to be very close to the input vector, right. We want y of I close to the input vector that we have, and we are kind of modeling this. So, if you think about composition of these mappings between the unknown system and the inverse model, these should kind of sort of cancel each other, and that is the basic philosophy behind inverse modeling. And examples of inverse modeling could be channel equalization in communication systems, or possibly echo cancellation, right. So, in the case of channel equalization, what happens, I have some signal that goes through an unknown channel, I do not know what the channel is, and I want to undo the effect of the channel, right. If I take the composition of the channel and this inverse model, that has to be close to a delta function, right, and this is what is the idea. So, and exact specifics as to what the input vectors are and what we want to drive, these are very case specific problems, but this is a high level schematic of an inverse model, right, because we want to model this so that our output at the end of the inverse model should be close to what we had at the input, right. So, this is the inverse modeling problem. Then control. So, I will sketch the block diagram again like what we did earlier, and then I will explain the individual blocks and how this works. Now, let us imagine that we want to regulate a plant, right. That means it is taking certain inputs from a controller, and this controller is controlled by the error of the signal, right. There is a reference signal that I want, and there is a reference signal, and because of the inherent properties of the plant and the controller, we have another signal which is not exactly the reference signal, right, and but we want to control the plant in a way it has to be regulated. So, this error signal, which is basically signal coming, which is a deviation of the signal from the reference signal and the feedback path, that is controlled via this controller. This is some transfer function that we want to regulate, and the regulated signal from the controller is fed to the plant, and any perturbance, disturbances, etc., they have to be kind of regulated within this feedback mechanism, right. This is a general sketch, and if you were to adapt this plant, this can be a neural network driven controller, right. This controller is where you want to do the adaptation. This can be neural network driven controller, right. This is a kind of a schematic of controlling a plant. So, plant is not the kind of biological plants we think about, this could be industrial plants, because for example, if I think about, let us say, the Haber process for manufacturing ammonia, some cycle is there and I want to regulate the flow of concentration of the gases into this plant, right. This regulation has to be controlled, and that controller can be a neural network controller, and how this controller works is based upon the error mechanism through an adaptation. So, I would just give this arrow here indication that it is some adaptation based upon the error that the controller sees. So, there are plenty of examples in real life. So, as we saw, there is pattern association, there is pattern recognition, there is functional approximation, and then control of plants, and these are all non-linear problems. There is nothing like an LTI system that is a linear and time invariant system like we are used to in traditional linear signal processing, where we can have a rational transfer function and we figure out through some parametric estimation how to capture the essence of the poles and zeros in the LTI system. Here there is no notion of these poles and zeros, right. These are all mappings, nonlinear mappings that we are trying to learn, and only under kind of approximations, when you take a piecewise linear approximation of this mapping, and at that stage we can analyze what the poles and zeros are, etc., with an appropriate LTI kind of model approximation to this mapping, right. Otherwise this is basically a nonlinear signal processing problem, mappings are nonlinear and we want to learn these mappings. So, this summarizes learning tasks, and this is the introduction to the neural network course as to what objectives we can meet through learning procedures, learning algorithms. In the next module we will start with the perceptron. This is the first basic algorithm that you will learn, and then our journey begins with the perceptron. Okay, let us get started with the perceptron. This is the first neural network algorithm or the model that you will learn through this course. Okay, there is a history to this perceptron. It is the first algorithmically described neural network, and the inventor was Rosenblatt, and this was in 1943, and that is why it is sometimes also called the Rosenblatt's perceptron. So, let us recall our linear combiner and the activation function we started a while ago. We have inputs x1, x2 dot 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 till xm. These are our inputs. Then we have weights connecting them to the linear combiner. Let us say these weights are W1, W2, so on till Wm, and we also have this bias. We have the local receptive field that goes through an activation function phi, and we have the output y, right. So, V is basically, if we recall, summation I equals 1 to m w sub I xi plus bias b. Now, what is our goal? Classify the externally applied stimulus into two classes called class C1 and class C2, right. It is a two class problem, and I want to classify the externally applied inputs into one of the two classes. So, if we delve a little deeper, what we want is a decision rule, and this decision rule is y, which is 1 when x is this vector that belongs to class 1, and minus 1 else when x belongs to x. There are only two possibilities. It is 1 when x belongs to C1, it is minus 1 when x belongs to class C2. Now, sigma I equals 1 to m w sub I x I plus b. If I equate this to 0, this is the equation of a hyperplane, right. If I have to sketch this, let us take a simple x1 x2 plane, and anything which is on the right side of this line is C1, and anything which is on the other side, left side of this line is C2. Now, we need to obtain the equation of the hyperplane. So, just for clarity, this is just a illustration. In R2, but our general equation is W transpose X plus this bias B is equal to 0 is the general form of this equation. But if you want to even fold this bias as one additional attribute, then it will have coordinates 1 to m plus 1, and you can have W transpose X equal to 0, and this bias you can treat this as a variable like Wi, but it is except that it is 1 times B, right. We saw that connection, right, but this is general form. Now, if I want to get W, so all I am given is X, these are my data points, and I know that they are linearly separable. That means, I can have a decision rule which corresponds to this function that I have written down, y is plus 1 when x belongs to C1 and minus 1 when x belongs to C2, and given this decision rule, and I can formulate a hyperplane, and I want to derive this equation of the hyperplane, that is I need to estimate and get W. So, this is where our journey begins, and we will discuss the algorithm and the proof of the convergence in the next module.